Okay, so welcome everyone, and thank you all for joining us for today's webinar. In lieu of this year's in-person best practice exchange, Efficiency Vermont is pleased to present this three-part webinar series to highlight critical energy efficiency technologies for businesses. These webinars provide expert guidance on lighting, variable frequency drives, and then today, and HVAC controls. And we've had sessions presented once every week for 3 weeks. And today is our third and final session with the topic of HVAC controls, what your control contractor and Efficiency Vermont can do to help you reduce HVAC operating costs. So we're very pleased to have today as our presenters, Alex Rowe of Efficiency Vermont and Nick Rock of Control Technologies Incorporated. So for today, if you have questions during the presentation, you can add them at any time to the Q&A tool, which is located at the bottom of the Zoom platform. Alex and Nick, though, will be answering all questions at the very end of the presentation. So please do add your questions when you have them, but again, they'll be addressed at the end. In addition, this session will be recorded and we will be posting this as well as the previous 2 sessions on efficiencyvermont.com. So feel free to access those and share those with your friends. So with that being said, I'm going to hand it over to Alex and Nick. So take it away.
Thank you, John. Can you hear me? Great, thank you. All right. Good afternoon, everybody. Happy November. My name is Alex Rowe, and I'm an energy consultant in Efficiency Vermont's commercial and industrial division, and I support businesses with energy efficiency upgrades and improvements to their HVAC and control systems. Joining me today is Nick Rock from Control Technologies. Nick is a former controls programmer, now an analytics specialist, with a lot of experience upgrading control systems in commercial buildings throughout Vermont with an eye for efficiency. Together in this webinar, Nick and I are going to discuss how your controls contractor and Efficiency Vermont can help you reduce HVAC operating costs through the optimization of control systems. And as John said, please feel free to use the chat feature in the Zoom platform to type in questions or comments as you think of them, and then we'll have roughly 15 minutes at the end of the presentation for Q&A. So here's the agenda for today's webinar. First, Nick is going to provide an overview of what HVAC controls are, so we're on the same page as we continue through the presentation. Nick will talk about how the controls industry has evolved over time, and then introduce us to today's standard in HVAC controls, which is called Direct Digital Controls, or DDC. After that, Nick and I together will share a couple case studies of recent controls projects in Vermont's buildings that yielded energy savings. And then I will walk us through the current program and incentive offers that Efficiency Vermont has for HVAC controls projects. And as I said before, we'll have time at the end for questions. And with that, Nick will start us off.
Excellent. Thank you, Alex. So as we get started here, one thing we want to do is just go over the basics of what are HVAC controls. So in our commercial buildings, we have all of our HVAC equipment, air handling units, boilers, fan coil units, and they're all meant to condition the space, whether it be for temperature, relative humidity, ventilation, for both the occupants and if there's any product in like an industrial building. So all of these HVAC equipment need to be controlled in some ways, and the devices used to control them are called controllers. These controllers all have inputs and outputs to kind of monitor the equipment and then to control the equipment. So just some examples of this. Inputs, we have temperature sensors, we have status points for fans and pumps, humidity. Output controls, we have relays, actuators, VFD signals. And so we kind of use these controllers with the inputs and outputs to control our HVAC equipment. So now we're going to move on to kind of the history of controls, kind of the pneumatic controls that started off, some of the standalone controls that you'll see out there. and then kind of show where direct digital controls came into play and kind of the advantages that they brought. So for pneumatic controls, I kind of call this the first network controls because they had one common compressed air that they used to control an entire building. So typically how the system operated was it used compressed air as both the control device to drive components like actuators and relays, and it also used the compressed air as the signal. So we would use that for thermostats and controllers to control the devices. These pneumatic controllers were typically packaged for specific purposes. So we would have a room thermostat controller that would control a valve or a fan. We could have a mixed air damper pneumatic controller that would have a mixed air temp sensor that would drive the outside and return air dampers. So these were very component based. As far as global control that the pneumatics gave us, they gave us the ability to do scheduling. So we could have our main pressure air that we're using for the system. We could change that pressure for unoccupied times, and all the control components would go to unoccupied control. This was a way that we could have one time clock control all of our equipment in the building on one schedule at a time. Some of the drawbacks of these systems was the fact that it had a lot of maintenance involved with them. Your pneumatic lines had to be kept clean and dry. You would have to make sure that your compressors are operating properly. A lot of the times the sensors had to be calibrated because they often drifted. And then you would need the expertise, whether in-house or through contractors, for any kind of service maintenance on them. Also, some of the disadvantages, whenever there was a change that you wanted, you would have to do physical reworking of the system. So if I wanted to change my air handling unit to run off of the return air temp instead of the supply air temp, I had to rework all of my tubing. And for other changes, you might have to even change out some of the controller types that you had to get the operation you were looking for. Also, the kind of the user interface, I say the control that you had was usually done through panels that were typically set up in mechanical rooms or some central location. And you would have a lot of dials and gauges, and that was your user interface into the system. So if there was any changes to set points, time clocks that you wanted to do, typically you had to go to these panels and operate it there. So now we kind of move on to standalone, or sometimes called package controls. These controls were typically done on a 1-to-1 ratio. So you would have one controller per piece of equipment. And a lot of the times it was a single zone piece of equipment. So you would have a VAV or an air handling unit for one zone. And that would be kind of the ratio. You would see it very common to use the traditional thermostat wiring. So you had fan call, heat call, stage 1 and 2, cooling call, same thing. And a lot of the control tended to be very simplistic, kind of on-off control. I could turn things on and off, but I couldn't really adjust things. I couldn't modulate things unless I had additional components. A lot of these programmable thermostats also had a 7-day schedule. So you would have to change for daylight savings time, leap years, that kind of stuff. If you wanted to do, say, some more modulating controls or some more advanced controls, you would typically have to use additional control boards or controllers to your piece of equipment. So if you had an air handler unit that you wanted to do economizer control with, you would take the normal cool call from your thermostat, bring it up to another additional economizer controller, and that controller would then have an outdoor air temp sensor and modulate the outside air if it was cold enough, or it would turn on some like DX cooling or chilled water valve. So you would have to have these additional controllers if you wanted to do some more advanced controls with your equipment. Some of the drawbacks to these standalone controllers that typically they didn't scale well and they didn't really network together. You could have some controls where they would have a kind of master slave setup where if you had multiple controllers, say for multiple air handling units for a large space, you would have one thermostat kind of be the master controller, and then all the other controllers would follow suit off of that. This kind of led to the reliance on one controller operating properly, and it also didn't give you any kind of ability to do like averaging between them or staging them. You also somewhat limited in some of the control sequences you wanted to do. If you wanted to say do like static pressure resets or something like that, you might be limited depending on the controller that you had. It either wasn't possible, or you would have to kind of do some workarounds and configure it in such a way that you get what you want, but it might not be the ideal installation. So now let's go over to DDC controllers and kind of show what the advantages these brought us. The diagram on the right is kind of a basic DDC architecture, and I'll kind of just go over that real quickly. You had your terminal controllers, your VAVs, boilers, air handling units, and these all these controllers were networked together with some kind of communication bus, whether it be a 2-wire communication protocol or IP-based Ethernet. And these networks now would come back to one supervisory controller. That supervisory controller would then feed all those terminal controllers up to the server and the graphical user interface, the GUI. Typically with the servers, you would have the ability to bring in multiple supervisory controllers as your facilities got larger and your BAS systems got larger. So with the early generations, our first couple DDC systems, when these first came out, these introduced the concept of programmable controllers. So now these were completely customizable. All the inputs and outputs could be changed depending on what you were looking for. The sequences could be programmed by a programmer, where now pretty much anything was possible as long as you had the IO and the logic blocks to do it within these controllers. It also introduced the ability to do networked variables or network values that could be shared across the network. So I could have the one outside air temp sensor on my boiler controller be shared with all of my air handling units for economizer control. I could have my one unoccupied heat set point be shared to all of my zone controllers and can be adjusted from the front end at once. These early generations were built on proprietary communication protocols. So a lot of manufacturers developed their own communication buses to talk to their controllers. And sometimes they would even have multiple communication protocols for the same product, depending on the type of controllers that they had. There was very little mixing and matching of these product lines. A lot of the times, once you were kind of invested in one manufacturer, if you ever wanted to bring in a different manufacturer, it would either be kind of standalone, or if you wanted to bring everything together, it was typically rip out all your older stuff and put in the new stuff. So there was no way to kind of mix and match between the product lines. A lot of these were also built on gateway devices. These were typically devices to kind of translate from one communication protocol to another communication protocol. As these systems grew and as the product lines came up with newer controllers, more and more gateway devices would be needed as you wanted to bring in the additional controllers. So it became a more complex network, and it introduced more failure points for your system. As your VAV controller is going up to the server, now it had to stop through a couple gateway and supervisory controllers in order to get there. These controllers, these early generations, also typically required specialized tools and devices in order to connect up to them to program them. Same with the programming software. You might have in the same product line different programming tools to work on the same controllers. This made it so your technicians and your contractors had to be well versed in all the different tools and have all of the different tools on hand. The early days also required a server that was typically running a software application on it that you would have to log into for your system. So even though we upgraded to a PC where now everything is kind of digital, we're still relying on that one PC located in the boiler room in the facility guy's office. And if you wanted to make any changes, you still had to get to that one location to log on to the system. All right, so now we jump to modern day and our current generations of DDC. These control systems are now built on common communication protocols. So we have our LAN, our Modbus, our BACnet. And so now we're on these open communication protocols that everyone uses. So it's a lot easier to mix and match. With these open communication protocols too, it became easier to build out our networks. We required less and less gateway devices. A lot of the time, we even have the ability to go straight from a terminal controller like a VAV and go right up to a server with no supervisory controllers or gateway devices needed because it's all IP based now. Our programming tools and our devices now become much more universal. So now you didn't have to have a tool bag of here's all the different tools I need to connect up to the controllers. Now we could have just a few for the different products and you could use them for different product lines. Our servers also started hosting web pages. So now instead of a physical machine that you had to get in front of to use your BAS, now the server could live elsewhere on the network. And as long as you could get to the network with a web browser, either from your phone, your laptop, you were able to get into the BAS system and do whatever kind of control you needed to do. Having everything IP-based also gives us more flexibility. Now we have the option of doing Wi-Fi. So a lot of the times in hard to get to locations, we can start putting in Wi-Fi controllers. We can also start doing stuff like virtual machines, cloud hosting. So now for our larger systems, our campuses, our multiple buildings, we can start having the server not even be physically located. It can live somewhere in the cloud. You have much more reliability with it that way. And now you can kind of control the scale of it. You can upgrade to it easier. We also have better control sequences that we can do now. A lot of the manufacturers started having ASHRAE standard programming sequences already implemented in them. So now instead of writing a program from scratch, a lot of the times they came with the programs you needed. You just need to configure it for your specific application. Made it easier to also deploy these controls. Now you had options for mass downloads, mass edits. So now your contractors and your programmers can easily set up very, very large systems quite quickly. We also now have the ability to integrate into more and more systems. So now we're reaching out beyond HVAC systems and into security and lighting systems. Now we can start looking at the access doors, and when people badge in, now we can know to turn on the heating and cooling and ventilation for their room, their office. And then finally, kind of looking forward into the future, the DDC and manufacturers are starting to add more functionality for data analytics and fault detection diagnostics, FDVs. These softwares are kind of the next step for BAS systems, where we're really kind of utilizing all the data that the systems have and kind of building off of it. And so now they either come with it already a part of the control system or easily to integrate into these analytic softwares. So with that background, now let's jump into some case studies, and I will hand it back to Alex.
Thank you, Nick. So as Nick said, we're going to dive into some case studies of recent HVAC controls projects that Control Technologies and Efficiency Vermont collaborated on to help customers realize energy savings as well as improve the overall operation of their HVAC systems. We'll start off with Hartland Elementary School, which is a 64,000 square foot building in southeastern Vermont that is home to roughly 290 students, grades kindergarten through 8th. The school is made up of, I think, 24 classrooms, which are heated, cooled, and ventilated by unit ventilators. Communal spaces like the gym, library, and cafeteria are served by a mix of unit ventilators and central air handling equipment. And heat is provided by a central oil-fired boiler system. When Efficiency Vermont and Control Tech began working with Hartland Elementary School, their entire HVAC system was controlled through pneumatics, except for the two air handlers that had standalone controls on them. The pneumatic control system operated on a single schedule using a time clock, but the time clock hadn't been touched in years. They had no visibility into what their temperature setbacks were, if they existed at all. And they had overridden the pneumatics on the air handlers and chose to run them manually instead. With a high upfront cost of upgrading or converting the building over to direct digital controls, Hartland held off on investing in the upgrade until the 2020 School Indoor Air Quality Grant Program came around and was able to provide a significant contribution to help make the project happen. Now, Nick will give you the technical details of the project.
Thank you, Alex. So for Hartland Elementary School, for the project, we had an existing pneumatic system with about 30 unit ventilators, 3 air handling units, the hot water system, and then miscellaneous zones like baseboard radiation, cabinet, unit heaters, exhaust fans. For this project, we've ripped all of the pneumatics out and replaced everything with new BACnet IP controllers. The school district had an existing building automation system that we were able to bring everything into. And being that it was BACnet IP devices on site, we didn't need any supervisory controllers or gateway devices. We were able to go directly to the server with the new controllers. All the pneumatic components were replaced, so sensors, actuators, brand new valves, for all the equipment. For the 2 air handling units that had standalone thermostats, we reused some of the actuators and relays, but added new sensors. We also had some unit ventilators with phase bypass dampers. Those are basically where the heating coil had no valve on it and would run hot year round. And then you would use the phase bypass damper to either bring the air through the coil or you would bypass around the coil. What we did for those units is that we fixed the phase bypass damper to 100% phase, so always going across the coil, and then added 2-way valves on the coil. So now we had better heat control in the space, and then also we're able to get some pump savings from shutting off those coils in the heating system in the heating season. The new BAS gave a lot of the modern day functionality that you'll see. So better user interface that they can access from anywheres, alarming, trend data, tighter schedules, more set point control. So it was a huge improvement for the facility staff there, going from the pneumatics to the DDC. We took the opportunity to do some additional program and sequence upgrades. So we added a max ventilation sequence to all of the air handling units and unit ventilators to bring in more outside air and better indoor air quality. We also added some tighter scheduling. So now instead of one global schedule for the whole building, we had each piece of equipment had its own schedule. So now we could get much granular control where we can shut down different areas at different times and get some savings that way. We also added demand-based resets for our hot water supply temperature set point and our air handling unit supply temperature set point. So for example, on the hot water system, we would typically have the outside air would be used to reset our supply temp for the hot water loop. Now it's actually based on the heating calls from the space. So as the areas needed more heat, it would reset the hot water supply temp up instead of just the outside air. A lot of the savings that we had in this project came from the scheduling and the demand-based resets, and also some of the pump savings from the 2-way valves that we added. So for more details on the savings, I'm going to hand it back to Alex.
Thanks, Nick. Yeah, so through all of the efficiency improvements that were made as part of this project, the school ended up saving 42,400 kilowatt hours of electricity per year, which is equivalent to a 17% reduction in their annual building electric load and $5,100 in annual cost savings on their electric bill. As Nick mentioned, the improved scheduling and hot water supply temp reset sequences saved on electricity, but they likely also saved on fuel oil. But unfortunately, we didn't have access to that data in order to quantify the exact savings. So here's a visual that really shows the impact of the controls upgrade at Hartland on the electrical use of the building. For those who aren't familiar, this is what we call a heat map. The horizontal axis is a timeline starting in 2017 up to October of 2021. The vertical axis is time of day, where morning's on the top and night is on the bottom. And the colors on the map show variations in electrical power, where dark green symbolizes lowest power draw and dark red symbolizes highest power draw. And then yellow is obviously in between. So as you would expect for a school, Hartland uses the most power from 8 in the morning to 3 in the afternoon when classes are in session. That's when lights are on, computers are being used, cooks are in the kitchen, HVAC system is running. And then in the early morning and at night, when the school is empty, power draw is much lower, hence the yellow-green color. And then the green bars along the timeline right here match up with summertime when school is out of session. The large green section over here with low energy use is the beginning of the pandemic, when school shut down in March of 2020 and stayed closed until the start of the fall semester in 2020. Now, Hartland completed their controls upgrade from pneumatics to DDC in January of 2021. As you can see on the heat map, there is a distinct change in power draw during unoccupied times, about 6 p.m. to 5 a.m. When you compare before here on the left of January 2021 and after on the right. And that difference, is that yellow on the left and the morning and nighttime versus more green on the right, morning and nighttime. So this difference is a direct result of adding and optimizing occupancy schedules for the HVAC system as part of that controls upgrade. And that's where Hartland achieved a majority of their energy savings, that 17% reduction in annual electrical use. Okay, so we've reviewed a comprehensive building controls upgrade, and now we're going to transition into a much smaller scale, but highly complex project that leveraged the facility's existing controls. So Springfield Hospital is a medium-sized critical access hospital, also in the southeastern part of the state, and it serves communities in Vermont and New Hampshire. The hospital's operating suite includes 2 operating rooms. The central air handling unit that serves the OR suite feeds 14 zones through variable air volume or VAV boxes, including the ORs themselves, as well as central sterilization spaces and prep rooms. To get a sense of size, the air handling unit has a 25 horsepower supply fan and a 5 horsepower return fan, and is capable of moving 15,000 CFM of air. Hospital HVAC standards require that operating rooms have 20 air changes per hour while occupied. So what that means is the entire volume of air in the operating room must be exhausted and then replaced with fresh outside air 20 times each hour. That takes a lot of energy to not only move that much air, but also to preheat or pre-cool the incoming outside air. So for that reason, among others, the hospital HVAC standards allow for operating rooms to have 8 air changes per hour when not in use, which saves on energy costs, as well as wear and tear on the equipment. When the hospital's engineering firm DuBois & King and their controls contractor, Control Tech, and Efficiency Vermont began working with Springfield Hospital, they were operating their air handling unit to provide 20 air changes per hour to the ORs 24/7. And reducing OR air exchange rates during unoccupied times is one of the most compelling energy savings measures that a hospital could invest in. So the team looked into how to make that happen. And with that, I'll let Nick explain the technical details.
Thank you, Alex. So for our operating room suite, we had an existing air handling unit that was already on the building automation system, and then 14 pneumatic VAVs, 2 of which was for the 2 OR rooms. And basically the whole system was 24/7 operation. So for this project, we ended up replacing the 2 existing pneumatic VAVs with BACnet IP VAVs. And then we added a bunch of components into the space, additional components. So we added our occupancy push buttons, our room pressure monitor, LED red and green occupancy lights, and then some door switches. So for this project, one of the first things that we ended up doing was doing an air balance of the entire system. So all the pneumatic VAVs and the air handling unit. We also ended up developing what the new CFMs were going to be for our unoccupied times for our 2 OR rooms. So for our new BACnet IP controllers for the ORs, we now had an occupied CFM set point that they would maintain, and then an unoccupied CFM set point. Similarly, we did the same thing on the air handling unit for the static pressure set point. We would have the occupied and unoccupied set points that we would use. Basically, for the operation of the schedule, we had a Monday to Thursday, 6 a.m. to 6 p.m. schedule introduced. And during those times, the air handling unit and 2 OR VAVs would run at their normal occupied CFM and static pressure set points. During unoccupied times, they would go down to their lower CFM set points for the VAVs and the lower static pressure set point to get our energy savings. Now, being an operating room, obviously we have emergencies come up, and when they had to do procedures, the staff was trained on how to get the system back into an occupied state. So there was the red and green LED lights that would indicate whether the room was occupied or unoccupied. If it was unoccupied, the occupants would go and push the push button, and then the VAV would go to its occupied CFM set point, and the light would indicate that we were back at the normal airflow rates. The air handling unit would also go back to its static pressure set point when one of the ORs went into occupancy. But we would also keep the second OR still unoccupied as long as it wasn't being used and it didn't have the push button pressed. So even during these times when we needed one of the operating rooms, if we didn't need the second one, we were still getting some savings from that one being at the lower CFM set point. So as far as the savings that we got from this, I will hand it over to Alex to go over that in more detail.
Thanks, Nick. So by optimizing the controls and operation of the OR air handling unit at Springfield, the hospital achieved 41,700 kilowatt hours per year in electricity savings just on the supply and return fan alone. That's equivalent to a 42% reduction in fan energy and a $5,400 per year savings on their electric bill. That does not include the electric savings on the chilled water system, nor the fuel oil savings on their central boilers from not having to condition as much outside air during unoccupied times. So there were definitely additional savings beyond just fan energy. So as part of the controls optimization project, Efficiency Vermont had sub-meters on the air handling unit fans to monitor changes in power draw. This graph starts in September of 2020 and ends in August of 2021, which you can see on the horizontal axis. The vertical axis is power, which goes from 0 to about 22 or 23 kW. The pink purplish line on the graph is the OR air handling unit supply fan, and the yellow line is the corresponding return fan. As we already discussed, prior to January of 2021, the air handling unit and OR VAVs operated to provide 20 air changes per hour all day, every day, which is roughly 7 kW minimum power draw right over here on the left. That increases during the day when the other VAVs on the air handler switch to occupied mode and react to heating and cooling calls. At the same time, the return fan maintained a constant power draw of about 1.5 kW, not varying speed whatsoever. In roughly mid-January to early February, that's when the hospital made all those changes, working with Control Tech, their engineer and their balancing contractor to replace the pneumatic controls on the VAVs and adjust control set points to reduce the OR's air exchange rate during unoccupied times. After that, you can see the significant drop in the base supply fan power from that original, excuse me, 7 kW down to 1.5 kW. And the minimum return fan power dropped from 1.5 kW on the left to about 300 watts on the right. Now the OR air handling unit's supply and return fan both vary speed to provide the necessary air changes to the ORs during occupied times and the minimum air changes during unoccupied times. As Nick mentioned, Control Tech installed occupancy push buttons to allow the hospital to switch to occupied mode when they had emergency surgeries during off hours. And you can actually see how the hospital staff has used those push buttons. So these smaller spikes here, where I've indicated in blue, are increases in supply and return fan power on a couple Fridays, which directly lines up with them pushing the occupancy buttons to switch into occupied mode. So I think that's pretty cool that you can see that. Overall, I'd say that this project was really successful. And in fact, the hospital is planning to upgrade the rest of their pneumatic VAVs to DDC next year. And we're excited to use this sub-meter data to see what additional savings come out of it. Okay, so now that Nick has talked to us about what HVAC controls are, specifically modern DDC controls, and we've shared some recent case studies, I'll walk us through how all of this could be applied to your facility and how Efficiency Vermont can support you. So as of 2021, this is Efficiency Vermont's approach to HVAC controls projects in commercial and institutional buildings, which we've designed to meet customers where they are. At the top, we have our recommended first step, which is either a controls assessment or a new controls preventative maintenance or PM contract to help determine the existing condition of a facility's control system and how a customer should go about improving it. Alternatively to that, a customer, if they already know what they need to do, they could just provide us with a proposal from their contractor or commissioning agent, and we can move ahead that way. Once a customer has completed an assessment or a new controls PM contract or submitted a proposal, we can support them with any control system improvements that are expected to result in energy savings. For most customers, that would look like repairing, retuning, or resequencing some of their controls. It could be diving into our existing building commissioning program, or it could be upgrading the hardware and software of their field devices, supervisory controllers, or server. Near the bottom of the chart, we have integrated systems and monitoring-based commissioning. And these offers are intended for customers whose systems are up to date and commissioned and functioning optimally already. Efficiency Vermont has standard incentive offers for controls assessments and new controls PM contracts, as well as existing building commissioning and controls integration. But the other three project types are currently custom, where we'll come up with an incentive that's based on projected energy savings on a case-by-case basis. And after supporting enough of these projects, we intend to have standard offers for all controls improvements. So with that being said, let's run through the details of each offer. So our incentive offer for controls assessments is 100% of the cost covered up to $5,000. The assessment must be completed by a controls contractor or commissioning agent in order to be eligible. And if the likely next step is an existing building commissioning study, then we would have to have that assessment completed by a commissioning agent. For new controls preventative maintenance, or also called proactive maintenance contracts, we can cover 100% of the cost up to $3,500 for most buildings, or $6,000 for complex buildings or systems. And for those of you who don't know, a controls PM is different from a mechanical PM. It's focused on the control system itself, and it must be completed with a controls contractor. For both of these offers, identifying efficiency improvement opportunities and providing proposals for making those improvements must be part of the scope in order to receive Efficiency Vermont incentives. Additionally, an assessment report or PM issue log must be completed and shared with Efficiency Vermont. And then once an assessment or PM is completed, we expect customers to consider investing in control system improvements where they make sense. So with that being said, some customers may, it may make sense for them to complete repairs or retune or resequence their controls. So that could be repairing components that affect economizer or VFD functionality, or adjusting set points and occupancy schedules, or adding in advanced demand-based control sequences like Nick was talking about earlier. RR&R projects are eligible for custom incentives that are based on anticipated energy savings. And then moving on to existing building commissioning, or EBCX, we used to refer to that as our retro commissioning program. Springfield Hospital's project actually roughly followed that EBCX process, just for reference. The first step is the controls assessment that we talked about on the last slide. And that must be conducted by a qualified commissioning agent if you're doing an EBCX project. So the next step is a deeper investigation into the HVAC control system, which is usually a collaborative effort between the EBCX agent and the controls contractor. And that involves troubleshooting, as well as developing an optimization scope of work and construction documents, like a revised sequence of operation. And the EBCX agent will also use trending and sometimes submetering to quantify energy savings that they anticipate resulting from that scope of work. Efficiency Vermont can cover 50% of the cost of this step, up to $15,000 as an incentive. Next is the implementation phase, number 3, where the controls contractor takes the scope of work and construction documents and implements them into the control system. Here, Efficiency Vermont comes up with a custom incentive offer based on the energy savings that were calculated in the last phase. And once implementation is complete, we'll pay out half of that custom incentive. The final step is commissioning or calibration, where the EBCX agent conducts functional testing to ensure that the improvement scope was implemented as intended, and writes up a final commissioning report. Once the report is shared with Efficiency Vermont, we'll pay out the second half of our custom incentive offer. Now we have equipment and software upgrades, starting with field devices. Efficiency Vermont can provide custom incentives for upgrading existing pneumatic or standalone controls to DDC field controllers, like Hartland Elementary School did. We can also support upgrading obsolete DDC field devices as long as they meet the criteria that's here on the screen. Supervisory and server upgrades include installing new supervisory devices and servers, upgrading outdated supervisory devices, and adding a web-based GUI where the server can be accessed remotely. For field device and supervisory and server upgrades, all incentives are custom and they're based on projected energy savings, which means that the upgrade scope of work must include some sort of efficiency improvements. So that's key. Just as a note here, we recommend that functional testing or commissioning be part of a controls equipment upgrade in order to maximize energy savings and ensure that everything is operating properly. Lastly, we have our more advanced project offers. Controls integration is what Nick talked about during his DDC introduction, where you could integrate your lighting control system or security system, but typically lighting control system with your HVAC control system, and allow you to leverage each system's infrastructure and optimize energy use. Efficiency Vermont can cover 40% of the controls integration cost upfront, and then another 10% of that cost 9 months after implementation, once we've received a controls report. Monitoring-based commissioning, or MBCX, is pretty advanced. It involves using regular pulses and trends of building management system data, as well as electric and fuel use data to identify and address issues in your HVAC system as they come up, and to find other opportunities for optimization. Everything about our offer for MBCX is highly custom. We'll cost share on the initial cost of setting up monitoring infrastructure, as long as the customer commits to acting on the deficiencies that come up. And we can provide additional incentives over time as each deficiency is addressed or is identified and addressed. So if you'd like any more information on Efficiency Vermont's HVAC controls offers, please feel free to visit our website at either of these links on this page. We also have some info sheets on each of the offers, as well as case studies similar to Hartland Elementary School and Springfield Hospital, which are available upon request. So that concludes our presentation. Thank you so much for everyone's time. And I think John is going to lead the Q&A session for Nick and I now.
Yes, great, Alex and Nick. Thank you very much. At this time, we don't have questions queued up, but this is the time and opportunity for folks to ask those questions. So in the next few minutes, please do chime in, put a question on the either the chat or the Q&A tool at the bottom of your Zoom screen. Nick and Alex can certainly answer them for you real time. If there aren't questions now and you may be watching this at a later time, this screen will give you Alex and Nick's contact information. So I'm sure they'd be willing to answer those questions at any time if you may be watching this at a later date and or time. So well, still nothing coming in. We'll give a few more seconds here while we do wait. If there's any questions, again, chime in with them, folks. But I will take this opportunity to thank Alex and Nick today for a great session on HVAC controls. Appreciate you, both of you, being on and sharing the information with us. So thumbs up there. And more broadly, I wanted to thank all folks who presented at our prior 2 BPX sessions. Well attended with great content. So if folks are on this call and may have joined us for prior calls, thanks to you all. Still no questions for this session, so I will just take the opportunity to put a plug for next year. These online virtual sessions were intended to replace our in-person best practices exchange. It went great, technology worked out well, but we really, really hope to have something in person again next year. So who knows what the cards may have for that, but we do want to see everyone in person. And while I've been jabbering on, we do have one question that came in. So are you able to see it, Alex and Nick, or do you want me to read it for you?
Do you mind reading it for us?
Sure. So the question comes from Robert, and he asks, for those that don't have cash flow to cover initial costs of upgrades, what is the suggested course of action?
So first of all, if you have a project that you're interested in, even if you don't have the cash flow, I would suggest submitting it to Efficiency Vermont and allowing us to work with your contractor and commissioning agent to understand the details of the project, so that we can see what incentives we can offer. Sometimes, depending on the project, we can offer design incentives up front to help with initial costs to overcome that barrier. And then in addition to incentives, we also have a business energy loan where we work, I can't remember the details of it. It's on our website, but we do work with a local bank to provide loans to businesses to support energy efficiency projects.
Excellent. Thanks, Alex.
Mm-hmm.
And Robert, thanks you as well. Okay. Last chance for any questions for Alex and Nick. And otherwise, again, thank you. We hope to see everyone in person in 2022 at Best Practices Exchange. We'll have more info coming on that once things shake out. It's a bit premature for that, but thank you for joining us today. Thank you for joining us the past 3 weeks. And with that, I think we will bid adieu. Take care. Thanks, Alex and Nick.
Thank you.
Take care.